We spend a massive amount of time on this show talking about the brains of modern technology.
Oh, yeah, we obsess over it.
Right, like the microchips, the AI models, the battery chemistries. We look at all the stuff that generates the power and the intelligence.
The sexy stuff, right? Everyone's talking about the engine, but nobody really wants to talk about the exhaust.
Exactly. But I was reading through the source material for today, specifically these technical papers and product insights from Eleanor Industries. And it really hit me that we rarely stop to think about the one thing that stops all that high-tech wizardry from literally melting down.
Which is heat management.
Right. Because ultimately, every device you own, every electric vehicle, every massive server farm is fighting the exact same enemy, which is thermodynamics. You generate power, you generate heat. And if you cannot move that heat away,
the system fails.
Yeah.
And actually, not just fails, I mean, it destroys itself. The limiting factor in almost all modern engineering isn't really how much power we can generate anymore. It's how much heat we can dissipate before the physics just breaks down.
So with that in mind, I opened this dossier from Eleanor Industries expecting, I don't know, liquid nitrogen or graphene heat sinks or some sort of futuristic active cooling tech.
Instead,
we are looking at round aluminium tubes.
It does feel a bit of a letdown at first glance, doesn't it?
A little bit, yeah.
Just round aluminium tubes. It sounds like something you'd pick up in aisle 4 of the hardware store to fix a patio chair.
It feels incredibly analog. I mean, we're literally talking about a hollow metal cylinder. But the more I read, the more I realized that this specific object, this geometry and this material is essentially the backbone of the green energy transition.
That is honestly not an exaggeration. Whether you're looking at the radiator in an EV or the condenser in a massive industrial chiller or a heat exchanger in a renewable energy plant, the core component doing the heavy lifting is almost always a precision-engineered, round aluminium tube.
So that is the mission for today's deep dive. I want to understand why. Why is the industry abandoning traditional materials like copper and steel for aluminium? And also, why is the shape so critical? Because to me, a tube is just a tube.
Well, that's the first misconception we need to clear up right away. In the world of thermodynamics and fluid mechanics, the shape is absolutely everything.
Let's start there then, because the source material talks a lot about circular geometry, and I kind of have to play devil's advocate here. If I am designing a compact heat exchanger for a car, wouldn't a square tube make more sense?
How do you mean?
Well, you could stack them perfectly flush against each other like bricks, right? You'd have zero wasted space.
You could stack them, sure. But once you start pumping fluid through them, you run into a major physics problem immediately.
Which is what?
Fluid Dynamics 101. If you push liquid or gas through a square pipe, the corners become dead zones. The velocity of the fluid in those tight corners drops to almost zero.
So the coolant just sits there?
Exactly, it stagnates.
Yeah.
And that creates turbulence and drag. In engineering terms, this causes what we call a massive pressure drop.
Okay, I saw that term pressure drop all over the Eleanor Industries docs. Break that down for us. Why is a pressure drop a bad thing?
Think of it like breathing through a straw.
Okay.
If the straw is a perfect circle, the air flows smoothly right. You breathe easily. Now imagine that same straw has sharp corners or weird internal angles inside of it.
You'd have to suck much harder to get the same amount of air.
Exactly. That resistance you feel that is the pressure drop.
And in a machine.
In a machine, that means your pump has to work way harder. A harder working pump uses more electricity, it generates more heat of its own, and it wears out much faster. A round tube offers the lowest possible resistance. It is quite literally the path of least resistance for the fluid.
Okay, so round is better for flow. That makes a lot of sense. But the sources also went deep into something called hoop stress. And that sounded like a basketball term to me, but I gather it's about durability.
It's crucial for durability. This is exactly why pressure vessels from propane tanks to submarines are round. When you pressurize a tube from the inside, the force pushes outward in every single direction.
Right.
In a round tube, that outward force is distributed perfectly evenly across every millimeter of the circumference. The stress is completely uniform.
And in my hypothetical square tube...
In a square tube, the pressure pushes against the flat walls, causing them to bulge out. That stress concentrates right in the corners.
So the corners become the weak points.
Exactly. Under high pressure, like you'd find in an AC condenser, a square tube is essentially trying to tear itself apart at the seams. A round tube is naturally holding itself together.
So the geometry isn't just about flow, it's about structural survival.
That's it. If you want a system that can handle high-pressure spikes without bursting the circle, is really the only geometric choice.
Okay, I'm totally sold on the shape. You have convinced me that circles win, but I am still a little skeptical about the material.
You mean the shift to aluminium?
Yes, I'm no metallurgist, but I remember high school physics. Copper is the gold standard for conduction. It moves heat faster than almost anything else. So if the entire goal of a heat exchanger is to move heat, why are we downgrading to aluminium? Aren't we making the system worse?
If you look at it in a vacuum, yes. Copper absolutely has higher thermal conductivity. If weight and cost were completely irrelevant, we would probably just use silver or copper for everything.
Yeah.
But engineering is never about optimizing just one variable. It is always about the trade-offs.
And the trade-off here is,
Wait, this is the killer app for aluminium. Copper is incredibly dense. It's very heavy. Aluminium is roughly 1/3 the density of copper.
1/3. That's a massive difference.
It is huge. Now apply that to the automotive industry. We are right in the middle of a revolution with electric vehicles. And what is the #1 anxiety for EV owners?
Range. Just how far you can go before the battery dies.
Right. And physics dictates that every extra kilogram of weight you add to the car requires more energy to move. If you build your car's thermal management system out of copper, you are adding dead weight that actively drains the battery.
So by switching to aluminium, even if it's slightly less conductive, you're saving so much weight that the car actually performs better overall.
Correct. You gain efficiency in the vehicle's range that far outweighs the minor loss in thermal transfer speed. And, by the way, engineers compensate for that minor loss by just adding a little more surface area or optimizing the airflow across the tubes.
So it's a quote-unquote good enough conductor, but a vastly superior lightweight material.
Precisely. It is the efficiency champion. But there's another property of aluminium that the Eleanor Industries source material highlighted, and honestly, this one felt a bit like magic to me.
Oh, the self-healing shield?
Yes, the corrosion resistance.
Walk me through this, because usually metal plus oxygen equals bad news. Iron rusts, steel corrodes. Why is aluminium so different?
It's a really fascinating chemical quirk. When iron is exposed to oxygen and moisture, it forms iron oxide, which we know as rust. Rust is porous and flaky. It physically falls off, exposing new metal underneath, which then rusts, and the cycle continues until the metal is just gone.
It basically eats the metal alive.
Right. But when aluminium meets oxygen, it forms aluminium oxide. Now, aluminium oxide is weird. It's extremely hard. It's actually the exact same material that sapphires and rubies are made of, and it bonds incredibly tightly to the surface of the metal.
So it creates a skin.
It creates a hermetic seal. It stops the oxygen from penetrating any deeper. It essentially passivates itself.
So wait, if I scratch an aluminium too, what happens?
The newly exposed metal reacts with the air instantly. It reforms that oxide layer and seals the scratch right back up. It heals itself.
That perfectly explains why the documents mention marine environments so much.
Exactly. Saltwater spray absolutely destroys steel. But aluminium just puts up its invisible sapphire shield and sits there. If you are building an HVAC unit that has to sit on a roof in Florida for 20 years, facing humidity and rain, that passive protection is worth its weight in gold.
It's interesting, though, because the source material makes a very specific point of saying they don't just use generic aluminium. They listed these specific codes like 3003 and 6061 and 6063.
Right, the alloys.
To me, they just look like serial numbers. But the engineers at Eleanor Industries treat them like completely different materials. What is actually changing between a 3003 and a 6063?
It is all about the recipe. Pure aluminium on its own is actually quite soft. So you add spices, basically other elements to change its personality. The 3000 series, for instance, uses manganese as the main additive.
And what does the manganese do?
It improves formability. Let's say you need to bend a tube into a tight pretzel shape for a condenser coil. You need the metal to stretch and bend without snapping or weakening. The 3003 alloy is formulated specifically for that kind of workability.
Okay, so the 3000 series is the bendy one. What about the 6000 series?
The 6000 series, specifically 6061 and 6063, is where it gets really cool chemically. For those, they add magnesium and silicon.
And that does what exactly?
When you heat treat that specific alloy, the magnesium and silicon combine to form microscopic crystals of magnesium silicide inside the metal's atomic structure.
That sounds incredibly solid.
It is. It acts like rebar in concrete. It significantly increases the structural strength.
Yeah.
So if you need a tube that acts as a structural frame or one that needs to hold very high internal pressures without deforming, you use the 6000 series.
So it isn't just aluminium. It's a highly custom tailored material. You pick the bending alloy for the coils and the structural alloy for the straight high-pressure runs.
Exactly. It allows the engineers to dial in the properties to the exact needs of the machine they're building.
I want to pivot a bit to the how. The what is impressive, but the manufacturing process they described, the extrusion, was just fascinating. The Eleanor Industries documents described it in great detail, and the analogy that immediately popped into my head was a giant high-stakes Play-Doh press.
Honestly, that is the most accurate way to visualize it.
Yeah.
It is exactly a Play-Doh press, just operating with thousands of tons of hydraulic pressure.
So walk us through that journey. It starts with something called a billet.
Right. A billet is a solid log of the specific aluminum alloy we just talked about.
Eh.
Step one is heating it up. But, and this is a really critical detail, they do not melt it.
Why not? Wouldn't liquid be way easier to just pour into a mold?
If you melt it, you're casting. And casting naturally introduces air bubbles, microscopic impurities, and inconsistent grain structures. Extrusion keeps the metal solid. It's just heated until it becomes soft and malleable. Think of it like warm taffy.
Okay, so we have a log of hot, soft, solid aluminium.
Then comes the ram. A massive hydraulic press pushes this soft log with incredible force towards a die. A die is essentially just a thick steel disc with a specific shape cut right out of it.
And to get a hollow tube, I assume there's a solid piece floating in the middle of that hole.
Correct. That's called a mandrel. So the soft metal flows around the mandrel and out through the ring-shaped gap. And because it was never liquid as it comes out the other side, the metal fuses back together perfectly under the pressure. This is what creates a seamless tube.
I have heard that term seamless pipe before. Why does seamless matter so much? Why not just roll a flat sheet of aluminium into a cylinder and weld it down the middle?
Because a weld is always a disruption in the material. It's a literal seam. Under high internal pressure or extreme thermal expansion, the weld is always going to be the weak point. It's exactly where the leak will happen. An extruded seamless tube is one continuous, unbroken piece of metal. It has uniform strength all the way around its circumference.
Yeah. There was one step in the manufacturing process that completely confused me: the stretching. The notes say that after the tube comes out of the press, they actually grab it by both ends and pull it. Why stretch it? Doesn't that make the walls thinner and weaker?
It does thin it very slightly, but that is carefully calculated. The primary reason for stretching is vital to the structure. When the metal comes out of the extrusion die, it is piping hot. It has to be cooled down rapidly to lock in those magnesium silicide crystals we talked about earlier.
Right, the rebar crystals for strength.
Exactly. But cooling metal that rapidly can cause it to warp. The temperature differential makes it twist. You could easily end up with a tube that looks like a banana.
Which is definitely not ideal for precision engineering.
Not at all. So they put the tube in a machine and stretch it just past its yield point. This mechanical pulling forces all the internal fibers of the metal to align perfectly straight. It effectively resets the metal's internal stress memory.
So it's primarily about straightness.
Straightness and stress relief. Yes. If you don't do this and you heat the tube up later during normal operation inside an engine, it might warp right back into its twisted banana shape. Stretching ensures that when Eleanor Industries ships that tube, it is dead straight, and it stays dead straight forever.
And I imagine if you are building a massive industrial heat exchanger with, say, 500 of these tubes tightly packed into a box, the dimensional tolerances for straightness have to be incredibly tight.
We're talking fractions of a millimeter. If a single tube is slightly bent, it won't fit into the header plate during assembly, or worse, it will vibrate against its neighbor while the machine is running and eventually wear a hole right through the metal.
Let's zoom out a bit. We've covered the physics, the chemistry, the manufacturing, but I want to land this plane in the real world for you listening. Where are we actually seeing these things around us? We mentioned electric vehicles.
The automotive sector is massive for this right now. Every single major EV platform is relying on aluminium heat exchangers to keep their battery packs in that perfect Goldilocks temperature zone.
But the source material also talked about industrial muscle.
Right. Think about data centers. We talk constantly about AI, and the cloud is just a massive physical building full of servers generating unbelievable amounts of heat. They use giant commercial chillers to keep those processors from physically melting, and those chillers are packed full of these tubes.
And what about power generation?
Very high stakes there. In a modern power plant, whether it's a natural gas facility or a concentrated solar thermal plant, you are dealing with immense pressures. A tube failure there isn't just a minor breakdown. It is a full facility shutdown. It costs millions of dollars an hour. The reliability of that seamless hoop stress-resistant design is literally the only thing standing between normal operation and catastrophic failure.
There's one last layer to this that I think is becoming totally non-negotiable for industries today, and that is sustainability. We hear a lot of buzzwords like green steel, but is green aluminum an actual real thing? Or is it just more corporate marketing
No,
fluff?
it's very real. In fact, aluminium is often referred to in the industry as the energy bank.
See, that sounds exactly like a marketing slogan to me. What does energy bank actually mean?
It means that while it takes a massive amount of electricity to refine raw aluminium from bauxite, or the very first time the electrolysis process is highly energy intensive, once you have that solid metal, it holds on to that value forever. Recycling aluminium requires only 5% of the energy that was needed to create new virgin element.
Wait, 5%. So it's 95% more efficient to just recycle it.
Yes, and here is the real kicker. Unlike plastics or composite materials, which degrade slightly every single time you recycle them, aluminum does not lose any of its structural properties. You can take a 6063 tube out of a 20-year-old car radiator, melt it down, turn it into a new billet, extrude it again, and the physics of the metal are exactly the same as day one.
So it really is a truly circular material.
It is infinitely recyclable. And since the global industry is actively moving away from copper, which is getting much harder and more destructive to mine, and moving away from plastics, which just end up sitting in landfills, aluminum is really positioning itself as the permanent core material for modern infrastructure.
So the, quote, replacement narrative, unquote, that the sources keep mentioning, this idea that aluminium is taking over the world of thermal management, is driven by cost performance and sustainability all at once.
It is the holy trifecta. It's incredibly rare in engineering that the cheaper, lighter option happens to also be the greener option. Usually you have to pick two and compromise on the third, but here you really do get all three.
So let's wrap this up. We started this deep dive by saying that heat is the invisible problem of our modern world.
And the precision round aluminium tube is the invisible solution.
It's funny because tomorrow when I get in my car or I walk past an AC unit humming on the side of an office building, or even when I look at a picture of a massive server farm, I am just going to picture those thousands of seamless extruded tubes hidden inside doing all the work.
They really are the veins of the machine, moving energy, managing the pressure, and resisting corrosion day in and day out.
But I do have to leave you, the listener, with a provocation. We have optimized the shape. The circle is geometrically perfect. We've optimized the material. Aluminium is clearly the champion. But technology never stands still.
It definitely doesn't.
As our AI chips get radically denser and our experimental fusion reactors get hotter, do we eventually hit a physical wall? Is there a hard limit to what a passive piece of extruded metal can actually do?
That is the billion-dollar question right now. Are we going to see new super alloys in the next decade where we dope aluminium with something like graphene to double or triple its conductivity?
Or maybe the tube just stops being passive altogether.
Exactly. Imagine a material that physically changes its internal structure based on the real-time temperature. Essentially smart thermal management.
Yeah.
Where the tube isn't just a static container, but an active moving participant in routing the energy. That is the next frontier.
Well, until we invent smart shape-shifting metals, we have the 6063 alloy and the perfect circle.
And they are doing a pretty incredible job keeping the world running for now.
A huge thank you to the engineering team at Eleanor Industries for providing the technical material for this deep dive. It has been a great reminder that the modern world is completely built on brilliant little details that most of us never even see.
Absolutely. Stay cool out there.
And to you, the listener, thanks for diving in with us today. Keep questioning how the world around you actually works, and we will catch you on the next one.